Okay, pre-calculus. I'm in my home studio and I'm trying this one more time. I'm on chapter 8. Should have something that looks like this. My packet says College Algebra Trig, but that's the old name for this course. It is a pre-calculus class. So we just changed the title when they merged the juniors and the seniors together. So this is going to look a little different. I've already tried this video twice. This is my third attempt, and I'm out of packets to write on. So it's the first page of it is already filled in, so to speak, but I didn't really get all that far because there's a lot of presenting stuff. So I'm going to open it up. It's going to have writing on it already, but you pause it if you need to. Basically, what we're moving into is what we have to do is they call them simplifying these little mini trigonometry expressions, solve some equations. They're going to look like this, and we got to simplify them. We got to make them look simpler than what they are right now. We got to use what's known as, I often refer to them as properties, but they are called trigonometry identities. Identities is the word they use instead of saying properties. Some of these we already know. So the reciprocal identities we already know. The sine of an angle. Now, instead of using theta or x in all these property boxes, they're using little u. All right, so you don't have to get confused by what does the u mean? The u is it's another way of saying x. I can write this with sine x or sine theta. It's the same idea. But the sine of an angle is equal to 1 over the cosecant. They're reciprocals of each other. And the cosecant of an angle is the same as 1 over the sine. So if I know the sine of an angle is 1/2, I flip it over for the reciprocal. The cosecant is 2 over 1 or 2. Cosine and secant are reciprocals of each other, these little fractions. Tangent and cotangent are reciprocals of each other. Those we already know, all right? Those are known as the reciprocal identities. And what happens in this unit, and this page will be more filled up when we get to the end of it. They're only giving you the beginning, the basic ones in the beginning. You get these little identities, and there's some more complicated ones down the road. You're just going to sort of get a feel for using them. That's the best way I can describe it right now. The quotient identities, quotient means divide, they're based off of what we know from the unit circle. So the tangent of an angle, we know from the unit circle, we could go, hey, that's y over x. We also know from the unit circle that the y is known as the sine and the x is the cosine on a unit circle. So tangent is often replaced with this little mini fraction, sine over cosine. So what I want you to do, if you're not writing down what I have in blue here, at least box this one. That's going to be an important one. Sine over cosine replaces tangent, or the reciprocal. Cotangent, we've learned on the unit circle, is x over y. The x being cosine, the y being sine. So we can replace cotangent anytime we want with this little fraction, cosine over sine. All right, now, a little more complicated. Let's go over here to the Pythagorean identity. Put a big little star. We use this one a lot. We use this entire box, but this top one, sine squared plus cosine squared equals 1. That might have even shown up on this year's SAT. It's that popular of a trig identity. It's based off of, the Pythagorean theorem, like a squared plus b squared equals c squared. In the unit circle, we use right triangles an awful lot. And so I drew one simple little right triangle. The y part is known as the sine of the angle. The x part is the cosine, and usually on the unit circle, the radius is 1. So sine squared plus cosine squared equals 1 squared. And that's where this comes in. Sine squared plus cosine squared equals 1 squared. Where the other two properties come in, and I'm not going to demonstrate. This one was easy to show where it comes from. But these other two properties, and don't worry about what's in purple just yet. You can leave that off for now. These other two properties, they come from, like, if they substitute, let's say for cosine, they put in 1 over secant, and then they started working. Or for tangent, they put in sine over cosine, and they simplify things and try to use this formula. Two other formulas that we'll use, and I'm going to use this third one in the example at the bottom of the page. But 1 plus tan squared theta, not theta, u, is equal to secant squared. So tangent and secant squared have their own little Pythagorean identity. And cotangent and cosecant, when they're squared, they have their own little Pythagorean identity. And you could put a little asterisk here. We're going to use that towards the bottom of the page here. Even odd identities, we don't use these very often. Actually, let me backtrack here. Since this is already written, I did this later on, but I may as well do it now. You guys are probably distracted by it. You could take any one of these three identities and rearrange them. Okay, you could rearrange them to make it fit what you need in a theorem or an equation you're working on. For example, I wanted to get cosine squared by itself. So I just take sine squared and I subtract it to the other side. So that cosine squared is equal to 1 minus sine squared. And I could use this parentheses to replace cosine squared or vice versa. And I demonstrated that down here. Let's say I want cotangent squared by itself. Just subtract the 1 to the other side. Then cotangent squared is equal to cosecant squared minus 1. I can take, if I see cotangent squared, I can replace it with this little parentheses, if that helps. All right, even odd identities. Let's move over now. Even odd identities, I don't recall using these an awful lot, but they're nice little properties to know. But basically, when can you move the negative out in front and it's going to come out to be the same answer? So this example, the sine of a negative angle is equal to taking the negative in front and just doing the sine of the angle. So like the sine of negative pi over 3 is equal to a negative of just sine of pi over, I said 3, but it's 2, pi over 2. I read that wrong. That's a 2. And then its reciprocal, it would do the same. So picture you just turn the fraction upside down. The cosecant of a negative angle is equal to a negative in front of the cosecant of an angle. Don't have to memorize these. You're always going to be given the property sheet, and that's something you could use as a reference. In fact, as we go through this entire packet, we're going to often say, all right, go back to your identity sheet. It's going to be this page, this sheet that we'll go back and look and like, all right, which one of these could we use? That's how you work with these identities. The cosine of a negative angle, like I did cosine of negative 60, that's going to be the same answer as just cosine of an angle. All right, they're going to be the same exact answer. And it has to do with the unit circle. If you did the cosine of an angle, it's the x value. If I did a negative angle and went this way, it's going to be the same x number. And that's where these two properties, cosine and secant, is its reciprocal. So if I did the secant of a negative pi over 4, that's the same thing as just the secant of pi over 4. You're going to get the same answer. But the way this worked for sine and cosecant is how it's going to work for tangent and cotangent. The tangent I did of negative pi over 6. It's going to be the same as a negative in front of tangent pi over 6. You can take that negative and put out in front and just do tangent of the angle. We don't use the even odds an awful lot. And on the next one, we don't use the cofunctions an awful lot. So these two, we're going to go through and we'll do some demonstrations of them, but not real worried about those two. They're not as big or as important for us. Cofunction identities is another way of saying, hey, these are the complement angle identities. I call them cofunction identities. Underneath where it says pi over 2 minus u. So if you have the cosine of an angle, that's going to equal the sine of the complement angle. This is 90 degrees, pi over 2 minus u. So it's an angle and it's complement angle. It's an angle and it's complement, tangent and cotangent, secant and cosecant. And all they're really demonstrating here, and then it goes backwards. If I did the sine of an angle, I kind of have this written backwards. I wish I did sine and then complement, but the sine of an angle is equal to its cosine complement angle. Picture a 3, 4, 5 triangle. 3, 4, 5 triangle, ABC. If I have A here and B here, and this is 90 degrees, no matter what degree number this is, this number will be 90 minus x. These two have to add up to be 90. They are complementary angles every time. So the sine of angle A, 3 over 5, is going to end up equaling the cosine of angle B, 3 over 5. Let's do that backwards. The cosine of angle A here, the cosine of angle A is going to equal the sine of angle B. So picture this as being like angle A, and then this is angle B. The sine of one is equal to the cosine of the other. The tangent of one is equal to the cotangent of the other, and the secant of angle A is equal to the cosecant of angle B. That's how this would work. It would be like the cosecant of angle A is equal to the secant of angle B, and you could switch A and B. That's how the cofunction identities work. All right, so last part, the important part. All right, what do we do with these trig identities and stuff like that? So try to switch out, try to have things cancel like fractions. Sometimes, often, this is usually a good way to do it, is try to make them all the same trig ratio. Make them all sines, make them all cosines, make them all cotangents, if that's what it is, something like that. So the first problem they give us is cotangent squared theta and cosecant squared theta. And the first thing that came to my mind was this Pythagorean identity right here, because it's got cotangent squared and cosecant squared. So I took cotangent squared, I got it by itself here. I got cotangent squared is equal to subtract the 1, cosecant squared minus 1. I replaced this top with cosecant squared minus 1. And I thought about doing this, like doing x plus 1, like doing cosecant plus 1, cosecant minus 1, but it didn't cancel anything below. All right, so I took cotangent squared theta and I replaced it using that identity, using this third of the Pythagorean identities. You got to figure out, there's got to be a way to make these two cancel, cosecant squared, cosecant squared. Well, I can't. Picture it being like fractions. If I had x minus 5 all over 2, I can call that x over 2 minus 5 over 2. I can separate them, pretend like we didn't combine the like denominators. So I'm going to do that here. And I'm going to separate that into cosecant squared theta divided by cosecant squared theta. You can see where that's going to cancel. Minus 1 over cosecant squared theta. When you have cosecant squared over cosecant squared, that becomes a 1. 1 over anything is going to be a reciprocal, so I go up to my reciprocal stuff. And 1 over cosecant is the same as sine. So this gets replaced with sine squared. Oops, sorry. This gets replaced with sine squared. Now this is a Pythagorean identity up above, and that's why those were written on the side. 1 minus sine squared is equal to cosine squared. So cotangent divided by cosecant, both squared. Your simplified answer is cosine squared. Oops, sorry, cosine squared. That gets a little confusing. It's a little tough, like, oh man, look at all that work. And I wanted to demonstrate where you could take something like this and separate the fractions like that. Sometimes that's the best way to do it. However, as soon as I got done with this page, I went, I think there was an easier way to do it. And I'm going to demonstrate that at the start of the next video. Click over to the next video for part 2 and the back page of these notes.